It is my privilege to introduce Dr. Carrie Womack. She is a research scientist at the NOAA Chemical Sciences Laboratory. And a lot of her research is sort of focused on measuring and understanding trace gases and aerosols in the troposphere and the chemical and physical processes that lead to bad air quality outcomes. She got her BA in chemistry at Bryn Mawr, 2008, followed by a PhD in physical chemistry at the University of Chicago in 2013, where she joined the CSL staff. She has worked on a variety of campaigns in her time there, including the 2016 Missoula fire study. A lot about what she's going to be talking about today, I think, comes from the 2017 Utah Winter Fine Particle Study that my grad school group actually participated in, which is exciting. But she also has taken part in the 2019 FireX campaign and has been telling me a lot about some really cool drone-based air quality instrumentation that she's been developing and working on, which sounds really interesting. And I think this is a really important talk that's clearly very related to my own research, since like I said, we're going to have a seminar speaker. But I think what's really cool about having Carrie here is that the paper she published that she's talking about today actually had a direct policy impact here in Utah, leading to the passage of State House Bill 220. We don't always have science papers that lead to policies being enacted. And so she's got a direct connection to that here. And with that, I guess I'll let you take it away.
Great, thank you. Do you want me to like aim it?
Whatever you want, yeah.
I think I might have to click back on.
Now we break it. You click on the current like PowerPoint thing.
Oh, there we go. Great. Okay. Okay. Well, yeah. So thank you very much, Jessica, for inviting me. It's always nice to be here. I spend a lot of my professional life looking at maps of Salt Lake City, and so it's always really nice to come in and see that it's all, the maps are right. So yeah, so it's really exciting to be here. I spent a lot of time thinking about air quality in Utah just because of projects that I've been involved in. So I'm going to tell you about a project that started almost 7 years ago and is still sort of continuing to evolve as we speak. So just want to start by, oh, it's because I turned this off. There we go. Okay. So I just wanted to start by acknowledging everybody who's worked on this. It's been a huge number of people. Some of them are actually sitting in this room. I'm sure I've forgotten or left people off here. So if I have, please accept my apologies. So this was a project called the Utah Winter Fine Particulate Study that was based partly on the NOAA Twin Otter aircraft, as well as some other ground sites. So that's pictured there, and then there's some acknowledgements for funding. And of course, we have really benefited from the collaboration with the Utah Department of Air Quality. So I'm just going to talk, start off talking about just air quality in this area and the campaign. This might be stuff that you already know, so I'll go through that kind of quickly. And although this is not really the topic of my, the main part of the seminar, I do want to just briefly talk about the first paper that we wrote about this campaign, because it really sort of lays the groundwork and helps us contextualize the results that we found about halogens. So then I'll talk about these industrial halogen emissions and their effect on ammonium nitrate particulate matter in the winter of 2017. And then I'm going to finish up just sort of advertising for an upcoming study next summer called USOS, with the Utah Summer Ozone Study. So starting with just some motivation. So you probably already know this, but PM 2.5 is a serious problem in the US, and particularly in the western half of the United States, with these two general areas highlighted. But if you just look at this map, it doesn't really tell you about the variety during the year. And so down here we have the last 20 years of daily PM 2.5 in gray, as well as the average in red. And so you can really see that PM 2.5 is a wintertime problem here in Salt Lake. And as you are, I don't have to tell you guys this, but the area is very mountainous, and because of its meteorology, experiences these persistent cold air pools or PCAPs in which a high pressure system moves into the valley. There's warmer air aloft and colder air down below that traps the air where the emissions continue to be emitted and react over the course of days or more than a week to form PM 2.5. Previous work that came long before us by some people in this very room has established that the dominant component of the PM 2.5 during these pollution episodes is ammonium nitrate, which comes from the reaction of gas phase nitric acid and gas phase ammonia. And it is typically true that nitric acid is the limiting reagent, that there's oftentimes an excess of ammonia. And so for the purposes of this talk, I'm going to talk mostly about, so what I'm trying to get to with this slide is that for the purposes of this talk, we can kind of say that, okay, well, the PM 2.5 problem is really a wintertime problem, which is really a ammonium nitrate problem, which is basically a nitric acid problem. So the motivation for this study was we wanted to understand what are the chemical mechanisms that form this nitric acid so that it can react with ammonia to form particulate nitrate, and what control strategies would be most effective for limiting nitric acid, because it tended to be assumed that NOx oxidation is the mechanism, and so therefore we should always just reduce NOx. So this was a study that took place over 4 weeks in 2017. We had the instrumented aircraft, which flew these repeated patterns throughout the area. You can see right here, it was colored by particulate nitrate on this one particular day. I think this was mid-January. And then there were also a number of different ground sites, and I've just highlighted the basics. There's a lot more going on here that had all sorts of chemical instrumentation. And a lot of people here were involved. And without going into all of the details of this campaign, because there really was a lot of work done, I would just say that during these 4 weeks, we did observe 2 major PCAP episodes. It was true that ammonium nitrate was the dominant component of PM 2.5, and it was true that typically ammonia was in excess. So therefore, 2017 was a pretty typical winter, and I would point you to a number of really nice papers that were published in a couple years after that, if you want to know more about this campaign. Okay, so that's the basics of the motivation and what we were doing there. So I'm going to first talk about what we ended up. So I'm going to talk about 2 conclusions that we came out of this paper. So to start with the first one, what I need to do is go into a little bit of chemistry. And if you're not a chemist, don't panic. It's not that bad. So the idea is that what's already known about ammonium nitrate is that there's this HOX-NOx cycle in which VOCs and NOx are emitted from a variety of sources, and they enter into this very nonlinear circular reaction mechanism where they can generate ozone. And traditionally, we have looked at OX, which is ozone plus NO2, because this is a very cyclical process where they're rapidly interconverting. So we can look at OX to see the net amount of this ozone, because there's daytime titration. But there's also some additional chemistry that's going on. So when you have large amounts of this NO2 and OH radicals, they can also form nitric acid. This is a termination step for this process, which then, as we saw, goes to particulate nitrate. And then there's also all of this nighttime chemistry. So the NO2 that exists at the end of the day can react to form NO3 and 2O5. That can be taken up on aerosol and make nitric acid. So there's really a lot of chemistry going on here. So the first thing that we wanted to look at was to expand this definition of where all the oxidates could go. So we started calling it ox total. That includes not just ozone and NO2, but also all of these other temporary reservoirs for that oxidant. So for example, NO3 and 2O5, ClNO2 is not even on here. Oh no, yes it is. And then nitric acid and particulate nitrate, and then all of these other temporary reservoirs, which are not in here. And the stoichiometry coefficients are to account for the fact that you combine an ozone and an O2 to make this. So this is equivalent to ozone molecules. So anyway, so when we think about it like this now becomes a parameter for basically the total amount of this entire chemical mechanism occurring. And so if it was if there's no net production any of those things, then Ox total would stay very flat. And what we found was that when we looked at the aircraft data on clean days, this was a typical vertical profile in the Salt Lake Valley where total Ox is shown in the black line, and then it's colored by all of these components. And it's really just all ozone. But a couple of days later, we did the same vertical profile into a pollution episodes. And what we found was that not only the total Ox had really started to grow close to the surface, but it also started to change in terms of its composition. So there was less ozone, but now there was more NO2 and more particulate nitrate, and it was more than just the chemical interconversion of NO2. So what this was indicating to us is that there is net production of total Ox, which in this case seems to be taking the form of particulate nitrate. So we also were able to observe this phenomenon from the ground. So this was a time trace for for one pollution episode. Again, black is the total Ox with some diurnal variations, and then it's colored by the various components. And you can see that this was the clean conditions. And then as the pollution episode started coming in, it really was converting all of that ozone to NO2 and to particulate nitrate. And this blue dot corresponds to the time of day that we took this vertical profile. So what this is an indication of is that there is seemingly some photochemistry going on, but perhaps that shouldn't be a surprise to us because, so we did this campaign in 2017. 2 years before that, there had been another campaign from our lab called the Uinta Basin Winter Ozone Study, or UBWOS. And that was located in the Uinta Basin. And what they found from that campaign was that photochemistry really was important in wintertime, which was sort of a surprise. But if photochemistry matters here, then it would make a lot of sense that it would matter here. So we started thinking about it in terms of wintertime production of these oxidants, whether it be ozone or particulate matter. So the next thing we wanted to do was to do a direct comparison between the Salt Lake Valley and the Uinta Basin, because they both experience these P-caps, which trap the pollutants. But what was happening was that in the Uinta Basin, it was forming a lot of ozone, whereas in the Salt Lake Valley, it was producing a lot of particulate matter. So when we plotted these in the same framework of this total Ox parameter, you can see that both of them are experiencing the same total growth in total Ox. It's just that in the Uinta Basin, it stays in the form of ozone, whereas here it's converting to, and this is turned into fractions, it's turning into a large component of both particulate nitrate and NO2. And so this leads to the question, well, why, two valleys, they're right next to each other, why should they be so different? And the answer is that they, despite being close to each other, they're actually very different. So Salt Lake Valley has a population, I think in the city of Salt Lake, it's about 1 million. So that's 800 people per square kilometer, no oil and gas natural wells. In the Uinta Basin, it's 2 people per kilometer. And at the time of that study, there were 10,000 active oil and natural gas wells. So what this means is that they are existing in 2 very different chemical regimes. And that's shown right here, where this is a log scale of the total VOCs and the NOx. And so the Salt Lake Valley is over in this corner. The Uinta Basin is over in this corner. So they have really, really different NOx to VOC ratios. And the reason that that's important is because the atmospheric chemistry world has long understood that ozone production is a very complicated nonlinear process, like the chemical mechanism I showed up front. It's a combination of both NOx and VOCs, but depending on what the ratio is of those 2 species, you can wind up in really different regimes. Okay, so to try and understand this, we used the DISMAC model, which is, if you've ever heard of foam or some of the other 0-dimensional box models, it's very similar to that. Pete Edwards, who had been a postdoc in our group, had successfully used this to model the ozone growth in the Uinta Basin. And so we were thinking, well, okay, if both of these valleys are both experiencing photochemistry, both experiencing growth in total ox, maybe we can use the same type of model to model the observations of particulate nitrate in the Salt Lake Valley. And so without going into too many details, when Pete did this, he was able to model the growth in ozone and also to place it in the context of this ozone isopleth, which if you're not familiar with ozone isopleths, they are a way of thinking about whether a system is more sensitive to reductions in NOx or VOCs, and it helps us understand where we stand in this complicated nonlinear ozone chemistry. And so what he had found was that the Uinta Basin was most sensitive to NOx. So just demonstrating that these are cross-sectional areas. And so what I did was I went and did a isopleth instead of looking at ozone, looking at total ox, but otherwise doing the modeling in a very similar way. And so what we found was that unlike here, where it was on the left side of both of these bumps, was that the current situation in Salt Lake Valley is that they're actually way in this NOx saturated regime, which means that when there's so much NO2, it's actually acting as a brake on the ozone production rather than an accelerant, because there's so much that it's just quenching the reaction of that ozone formation. So this was sort of unusual to figure out, because what it was saying was that actually the Salt Lake Valley is most sensitive to VOC reduction. So the way that you would look at this plot is to say, okay, so if this is our normalized NOx emissions, if we start lowering the NOx emissions, the total ox, which in this case is mostly going to be particulate nitrate, is actually going to go up at first quite significantly before it starts coming back down. Whereas if you were to reduce the NOx, the VOC emissions, then you would see a more immediate decrease in the ammonium nitrate. So this was a bit surprising to us because, like I said at the beginning, it had been long sort of assumed that particulate nitrate is most sensitive to NOx reductions, but what we were showing is the opposite, is that actually VOCs are the thing that you would want to target unless you're doing them both simultaneously. So that was where we stood we published this paper in 2019, and actually in the years since, there have been a number of papers showing that the same thing is true in a lot of other places. So the chemistry that plagues Salt Lake City in the wintertime is actually very similar to the chemistry that's going on in a lot of urban areas in East Asia. So there's been a number of studies in, say, Beijing that are showing this exact same effect, that for years, everyone had assumed that to reduce the particulate nitrate, you want to reduce the NOx, but actually VOCs are a really important part of this. So
is that also in other seasons?
It's mostly in the winter. I think in Beijing, in most places, the winter time seems to be the PM 2.5, and the summertime is the ozone problem. But I think what we were demonstrating with this is that ozone and PM 2.5 in the form of ammonium nitrate are actually very similar to each other. They both come from the same NOx VOC chemical cycle. It's just that some places and some times experience high ozone, some places experience particulate nitrate. So that also gave us a new way to sort of think about particulate nitrate in terms of these isopleths, and that let us think about what would be the effect of lowering emissions in the area. So so that's the end of this section, which I think is a bit of a tangent, but I'm going to come back to those results after I talk about the halogens, because now that we've discussed that, I think it makes a little bit more sense to try and understand what's going on with the halogens. Okay, so what happened was that we published this paper, and then we sat around, and in the spring of 2020, we were going to have a student come out to our lab and do a summer internship, and then COVID happened, and we needed to pivot to a data management project. And so we said, hey, there was some weird stuff happening during UWFPS that we never got a chance to look at. Can you look at it for us? And she did, and it was very interesting. And so we kept looking at it. And she did such a great job that she's actually now a graduate student in our lab. So she's doing her PhD after doing her summer internship with us. And what happened was that on the very first flight of UWFPS, January 16th, we had been advised that the US Magnesium plant, which is shown over here, is known to be an emitter of various pollutants. And so we were advised it might be worthwhile to take your instrumented aircraft and fly over there and just see what's going on. And it was so fascinating that we went back on 9 different flights. And it turns out that I'm really glad that we did, because the things that we learned have been quite illuminating. So I'm going to tell you the story of what we actually saw. So we flew, our plane came around here, did a loop, and then flew back here and came over here. And this flight track is colored by ozone. And you can see that normally ozone is in the sort of 40, maybe 45 ppb region. Around here, it dropped to 0. So you can also look at this as a time trace, where the red is the ozone as we were approaching the plant. And then all of a sudden, steep drop off that goes to absolutely 0. And then we climbed the plane a little bit, it recovered, we went back down, it went away again. And then as we flew away back towards Salt Lake, it recovered. Now, ozone titration is not a completely new concept. It is true, like I was saying before, that ozone can react with NO. It's called NOx titration. And so normally you can get around that by looking at the sum of ozone and NO2, because if the ozone gets titrated, it will just convert to NO2. So usually they are anti-correlated with each other. But this blue trace shows the NOx, and you can see that it maybe went up to 5 ppb, but nothing like the 50 ppb of ozone. So this had to be something else. And at the same time, because we had an iodide SIMS on board, we were able to see that the mixing ratios of these 3 halogens, Cl2, BrCl, and Br2, were sort of shockingly high. So for context, this peaked at 10 ppb during the day, and Jessica will tell you that's extremely high. That's like
Highest ever recorded.
Highest ever recorded.
Yeah, order of magnitude.
Yeah, that's like check your instrument to see if it's high. And you really, while there's a number of chlorine sources, bromine sources tend to be rarer. And this was up to 3 ppb of bromine, which is just sort of wild. But what was really fascinating is that we went back at night, and when we approached the same plant, what we see is we actually do see some of this NOx titration. So you can see that the ozone goes down, but at the same time, the NOx goes really high up. And simultaneously, we are seeing 600 ppb of chlorine, which is volcano level, I think. Just like astoundingly high. And granted, we were very, very close to the stack, and there's always going to be dilution. But what this was indicating to us, because this only happened during the day, and because there was no evidence of significant NOx titration, this very strongly points to photochemically produced halogen radical induced ozone depletion. So I'm going to go through the chemistry of what that actually means. So you may already be familiar with some of this chemistry, because this is the key chemistry that governs the ozone hole. The chlorine atoms are released from these long-lived CFCs, which come up from the troposphere into the polar stratospheres, and then they react with the ozone to destroy the ozone, and then they can react with each other to reform the Cl2, which then enters into this cyclical process. So that's the chemical basis for the hole in the ozone layer. It's also a well-known phenomenon in the tropospheric Arctic regions, because there's not a lot of other anthropogenic sources. So here it tends to be more on the bromine side. It's called the bromine explosion. That's observed every spring in the tropospheric Arctic. And there it's more about bromine, and there's a solid phase reaction that has to occur, and it's the primary source there is the sea salt, but it still enters into this sort of analogous reaction where the photolysis generates these bromine radicals, which then destroy ozone to make BrO, but then it can reform and the process continues. There's another way of thinking about this, which is in the tropospheric mid-latitudes. So in the continental US, for example, there's a known, it's very well known that there are these sources. There's ClNO2, which it's a little unclear what all of the tropospheric halogen sources are, but it does enter into this same process where the ClNO2 is then generating the chlorine radicals. And we know that chlorine is very reactive with VOCs and with NO2, and there's all of this N2O5 uptake, but the same basic chemistry occurs here. And this is known to be a method for transporting chlorine from the ocean to reservoirs inland, and it does have effect on tropospheric oxidation chemistry. So it's not as though halogens in cities was an unknown phenomenon, but what was different about the Great Salt Lake was just the magnitude of it, and also the emissions. So this is now the same chemistry. However, the primary source is this diradical halogen species, which is then being emitted, reacting with, and then the radical can then react with ozone and do the same process. But now there's all of this other chemistry going on because there's such a huge amount of these dihalogens that they can now react with all of the other things that are going on in the city, primarily the VOCs. And so what we wanted to do was take the known chemistry, because that's been fairly well established, and put it into the context of what we were seeing in Salt Lake City. And so another question that I also get asked is, how sure are you that US Magnesium was the source? And I have to say, like 100%. There's nothing else out there. And I will even say that Lexi Goldberger, who some of you know, was on board one of these days, and she took this video, which I'm going to try to. Yeah, so this was at night, and that's the plant. And you see that smoke plume? We went through it. You can smell it. And that's where the spike is, like bleach. Okay. Yeah. So yes, so through a number of sources, we are quite sure that the plume coming out of that plant is where these halogens come from. So the first thing that we wanted to do was to try and understand what the emissions were from this plant. So this was the work that Wyndham Chase, our former summer intern and now current grad student, did. She did a great job. And so what she did was to take all of our nighttime flights when the photochemistry turns off, and just take all of the times that the plane flew straight through the plume. And so what you can do is you can just assume that it's roughly cylindrical. And so if you fly through it and say, okay, this is the wind speed, the total amount of mass in that disk has to be the flux that's coming out of the plant. So she did this for about 14 different plumes. Some of them we were not going straight through the plume, so we had to reject those, but we got an average of all the times that we felt like we were going straight through the middle of that plume, and came up with an observation-derived emission flux. So basically what we measured from the plane, and that's shown here for these 5 species. They also emit NOx, so we included that as well. And so the number, as you can see, is over here, and then we compared that to what the facility itself reports, because they have to report their chlorine emissions to the EPA. And so you can see that we measured 90, they said it was 114 grams per second, which is, a pretty reasonable agreement, given that there's a lot of uncertainty in how we're doing this, and also the fact that this was assuming that it's a constant emission rate throughout every second of every year is the same, which is probably sort of an approximation. So we were happy with this. The fact that we were able to use this method to approximate the chlorine emissions gave us a lot of confidence in our bromine emissions. Now, the thing about bromine emissions is that they are not reported to the EPA, because the EPA does not ask anybody to report bromine emissions, because they, I think, didn't know that it's a little unclear. It's not one of the listed pollutants, and so nobody reports it, and so then the EPA doesn't know about it, so they don't ask about it. reports it, etc. But we also got good lineup with their NOx emissions. But if you take this total amount that we were seeing in terms of grams per second and scale it up to the entire year, what that essentially meant was that we were estimating that they are emitting 2.5 million pounds of combined bromine and BrCl. That's a lot, maybe not for other species, but these are very highly reactive molecules. And just for context, US Magnesium reported that they emitted 7.9 million pounds, which is more than the rest of the US combined. They are between 50 and 85% of the total chlorine emissions on any given year. So if they are that high for chlorine, I would imagine that they are probably the highest bromine emitter. But again, there's no EPA record, so can't know that for sure. Okay, so once we had sort of established the approximate quantity of those halogen emissions, the next thing we wanted to do is say, what is the effect of those emissions on the Great Salt Lake Valley? So in this plot over here, what I've plotted is a log scale of the chlorine. And then over here, I have a log scale of the ox. And the reason that I did that, this is the ozone plus NO2 to get around any of that intercomparison between ox and NO2. And what you can see is that the chlorine, and this is true about the other halogens, is that it's very centralized near the plant. And as you get closer into these populated areas, there really just isn't that much. You know, we're talking a couple ppt, which is not too crazy because it really does dilute and it reacts. However, the markers of that chemistry are obvious when you look at the ox, because we saw that the ozone gets removed by these halogen emissions, and then there's all of this subsequent chemistry. So what you can see here is that normally the ozone is at about 45, so maybe orange, but all of these darker colors, the reds, the blacks, indicates that there is still halogen chemistry, halogen-induced chemistry happening as the plume goes from US Magnesium across the Great Salt Lake to these populated areas. So the next thing that we wanted to do was to quantify this a little bit better, but to do that, we needed to quantify the plume ages. And here we have John Lynn to thank because he used the stilt model and ran this model every 1 to 2 minutes for every single Twin Otter flight, which is a lot of trajectories. And he's the real expert on stilt, but basically the idea is that you release 200 particles and then follow them back in time, given the meteorological, the wind speed parameters that were present at that time. And so it's a way of sort of imagining where a parcel of air came from. And so, for example, this was a flight where right here we were measuring, low ppb levels of BR2. And so when we looked at the trajectory flight, you can really see that the model is indicating that air mass was probably influenced by US Magnesium. And there's a number of other examples. I've just showed 2 examples. As you get further and further away, it can be a little bit more, it's not always as easy to tell, but like, for example, this is another example where we saw these 3 peaks in bromine. And when you run that trajectory back, it really just seems very obvious that there is some influence from the US Magnesium. So once we had all of these stilt model trajectories to work with, we were able to convert those into ages by just saying, okay, if this air mass is here, how long ago was it near US Magnesium? So we were able to use his model to convert all of our observations into plume ages. So now you can see that these same observations are colored by plume age. So the lowest ones are 1 or 2 hours. By the time we get out to these populated areas, these tend to be more like 10 hours old. But we did that for all of these flights where we observed influences from US Magnesium. For example, on January 18th, we intersected this plume this many times at a range of plume ages. And so then our next step was to start inserting this into a box model so that we can understand how is the chemistry changing between when it gets emitted from the plant to when it arrives at Salt Lake City. So there we go. So we used the foam model, which is like DISMAC that I mentioned before. So it's another example of a zero-dimensional box model. It basically it allows you to have a lot of chemical detail in this model, and it allows you to look at the progression of chemistry as it moves downwind in time. Now, I have to take a quick digression here. If you're familiar with box modeling, this might be relevant for you. If you're not, don't worry about it. But typically, aircrafts do this thing called Lagrangian sampling, where they go by a source and then they try to match their wind speed, their plane speed with the air mass wind speed, so that they can keep measuring the same thing over and over again. We were not able to do that just because the wind speeds were sort of low. So we had to utilize what we were calling the puff model, which Wolf at NASA developed, where basically we had to run, to get this, we had to run 5 identical models, one that ended up here, one that ended up here, etc. So we used 5 parallel models, initialized them the same way, but they started progressively earlier. So anyway, so that's the end of the digression. If that matters to you, I can talk to you more about how we implemented it. But basically, we used this model with the other parameters listed here. So we're using the MCM, which is a very detailed chemical model for understanding VOC oxidation. We used some halogen reactions that were combined from a lot of different sources, which I can also talk about more. And then the other parameters are listed down here. I won't go into all of the details, but the idea is that we were initializing it and tuning the model parameters until it matched our observations. So we were able to do that. So for example, we can see an example of the puff model, as well as the sort of the combination of all of those individual models, as we were able to recreate the chlorine, bromine, BrCl, and the ozone. So we were able to confirm that the chemistry going on is this halogen-induced ozone depletion, and that we were able to watch it as it came downwind and the ozone eventually recovered. So that was really good. But then the question for us was, okay, this is all excellent, but what does this actually mean for air quality in Salt Lake City? Because the fact is that over these couple hours, this plume is being transmitted usually across the lake, because that's the prevailing wind direction. And then it reaches the populated Salt Lake City region, which has its own set of pollutants. And so what happens when that chemistry mixes with this chemistry? So I'm now bringing us back to the first topic that I talked about. This is why I wanted to talk about this, is because now we've introduced a new feature of this. Because in addition to the VOCs generating these oxidized VOCs and these highly reactive radicals, there's now another mechanism, and it's the chlorine and the bromine radicals reacting with VOCs to generate these radicals, which then accelerate this entire process. So this is why it was important to us that we had already figured out what was going on to form particulate nitrate, because I don't think we would have really understood why, chlorine radicals, what do they have to do with particulate nitrate, which has no chlorine in it? Why, how are those two related? And the key is that the chlorine and bromine are sort of acting as catalysts. They're not adding to the PM2.5. They're simply accelerating the chemistry so that other things make the PM2.5. So the most logical next step was then to run our box model in 2 ways. One, normally, which is with the yellow, and then to remove those halogens. In other words, we did a model imagining that US Magnesium doesn't exist. What would happen to those chemical pollutants? So we were showing it in terms of these HO2 and RO2 radicals, as well as the formation of nitric acid, to demonstrate that the chemistry that we think is going on is really changing the outcome of those chemical species. So after 6 hours, we looked at the total concentration and found that there was a significant reduction in all of these species if you don't have those halogens there. However, this is just one way to look at it. It's necessarily sort of simplified, and it's only looking at the chemistry inside that plume. But in reality, of course, that plume is going all over the place, and the dynamics of the Salt Lake Valley are more complicated than that. So I worked with a modeling coworker, Siwan Wong, who is an expert in the CAM-CHEM model, and so he was able to reproduce a very similar result and generated these really nice figures that showed the difference between a model run with halogens and without halogens. So analogous stuff here, but now looking at the full spatial distribution. And so the key figure that I want to show is this one over here. And what it shows is the mean difference in surface PM 2.5 over one pollution episode with the halogens and without the halogens. And it's colored from the reds are all increases in PM 2.5 with those halogens. And depending on where you are in these valleys, and particularly in these populated areas shown with the black outline, that corresponds to what we decided to call 10 to 25% increase in PM 2.5 as a direct result of this one source, which is a very strange result in atmospheric chemistry. You're not usually able to tie such a dramatic change in the air quality of a city to one particular facility. It's usually a group of point sources. So we published this paper on January 25th of this year. Within the next couple of days, I am told that there were a number of news articles that came out about it. On February 15th, HB 220, which Jessica alluded to, was a House bill going into the Utah State Legislature that was going to make some recommendations for general air quality and emissions. But it was rewritten, I guess, as a result of the paper that we published to focus specifically on bromine. I was asked to testify, I guess, in front of the Utah House subcommittee about this. I answered some questions for them. The bill made it all the way out of all of both the House and the Senate subcommittees, and then it passed on March 4th and was signed on March 14th, so less than 2 months later, which was unbelievably fast. Even like nobody at our lab can believe it. And what HB 220 is that it mandates that a state compile a bromine inventory, not just from US Magnesium, but from all industries. And so what this, I mean, politics aside, more information is good. It will be really, really helpful for us to understand what the plant or what any plant in the area thinks that it is emitting in terms of halogens. And it also leads to another question is, if we've never asked about bromine before, we happen to see this one source, what other sources might be out there? Okay, so that is the story on halogens. I don't know how I'm doing on time. Okay, so in these last few minutes, I am just going to talk about what we're doing now, because what we have learned from this experience is that we came in with our instrumented aircraft, and we were able to learn a lot of really great information about wintertime PM 2.5. But wintertime PM 2.5 is not the only air quality concern in Salt Lake City. As you know, summertime ozone is also a major concern, and it seems to be, if not getting worse, then certainly not improving. And so we've received some funding from UDAC to conduct the Utah Summer Ozone Study in the summer of 2024. So I'll just talk a little bit about that, as well as share with you some very, very preliminary results from a flyby of Salt Lake City that we did a couple months ago. So I'll tell you about that as well. So as you know, the problem here is that Salt Lake Valley, I believe, has now moved into moderate non-attainment, but is expecting to be in severe non-attainment with the 8-hour ozone standard. It seems to be possibly getting worse, and it's possibly due to growth in population, changing emission profiles, the influence of wildfires. It's really not clear at this point exactly what's causing this ozone growth, or at least the absence of improvements in ozone, given that technology keeps getting cleaner. So cars are getting cleaner, technology is getting cleaner. So we are coming back to answer some of these outstanding questions. So what are the emission sources of the ozone precursors. So like I said, just like PM2.5, the causes here are NOx and VOCs, but those are two very broad categories. Where are they coming from? When are they getting emitted? How are they spatially distributed in the valley? Are there other chemical mechanisms that we're not aware of that are responsible for some of this ozone? What is the role of meteorology and boundary layer dynamics? People in this room will know more than anyone that the Salt Lake Valley is very hard to model because of the complicated mountainous terrain. And what is the role of long-range transport of ozone between valleys? What's the role of wildfire smoke? So we'll be back nominally July 15th to August 15th of next summer with the purpose of trying to understand this growth. We will have a mobile lab, and we will be combining that with WRF-Chem modeling and a Twin Otter remote sensing aircraft. And we're going to be targeting all of these species and doing repeated drives throughout the valley. So
what is moderate non-attainment?
So there's different classifications of non-attainment. I think it's, so you're either in attainment with an air quality standard, meaning you're below it, your air quality is good. You can be in marginal non-attainment, moderate non-attainment, or severe non-attainment. And those are just categories of how far beyond the air quality standard are you. And for a while, I believe this area has been marginal. They've just moved up to moderate. They're going to be moving up to severe.
It comes with like EPA requirements of
Yep.
how much you have to prove with what you're doing to clean up your air. So it's a lot of work for the state if you go into a higher non-attainment category. The things that we have for sure, because this is still an evolving campaign, it's one of the things I've been talking to a lot of people about today. But the things that we know for sure are going to be there is that we have a modified sprinter van that will have a relatively complete suite of chemical instrumentation. So we'll be measuring NOx and ozone, VOCs, formaldehyde, greenhouse gases, aerosol, halogenated VOCs and OVOCs, which are a lot of the key ingredients you need to understand ozone formation. And we'll be driving through the valley and also being parked at a ground site for the rest of the time. We are bringing our Twin Otter aircraft, which is going to have a Doppler LiDAR, which can measure horizontal and vertical winds and aerosol backscatter. So it's going to be flying above the city and just scanning the whole area, looking at the boundary layer dynamics, because that's a really key part of constraining how these pollutants are moving around the valley. We would love to get, we're trying to work out an in-situ chemistry package and a column trace gas package, but I can't promise anything there. And then of course we work closely with our WRF-Chem modeling teams, and they are going to take all of the observations that we take next summer and try and build them into more complete models so that we can understand ozone in this area. We're also going to use the fact that the Utah and Salt Lake valleys are very well instrumented. There's been a lot of air quality work here that we want to build on. So I've just highlighted some of the things that are currently going on that we'll plan to utilize, including the tracks measurements, the buses, the helicopter air quality sensors, the ozone network in these valleys, the purple air networks, the existing UDAC monitoring sites, MESO West, and of course, the recent advance in North American air pollution monitoring. I'm not sure how many people in this room have heard of the Tempo satellite. It was launched it was launched 6 months ago. It just started taking data preliminarily on August 1st of this year. By next summer, it will be fully operational and all of that data will be available. It is hourly column measurements of NO2 across the entire North America, which is really amazing. For many years, we've been putting up or doing what we could with orbiting satellites that only passed over an area at about 1:30 in the afternoon. This is going to be daily coverage, hourly, of a lot of different air pollutants. And this is going to be one of the first campaigns that occurs completely under the Tempo satellite.
Excuse me for interrupting, but that observing site up in the wetlands, the very environmentally sensitive wetlands there.
Yeah.
That you have unfortunately labeled the inland port. The inland port is something that any environmentally aware individual is fighting tooth and nail.
This one?
Yes.
Okay. Did I label it?
We're not fighting the monitoring site,
Uh,
but the inland port
oh, yes.
is an atrocity that we are fighting.
I'm aware that it is controversial, and that will be something that our mobile lab will be able to drive around and see what we see. Yes. Okay. Yeah, and I would just say that at this point, it is still an evolving campaign. We're really hoping to develop some other instrumentations. There's a lot of stuff that's sort of, maybe we're just talking about it, so I haven't listed that here, but we're really hoping for a really great ground site that builds on everything that people in this area have been working on for years, and just brings in some extra equipment. So I'd love to talk to anybody about that who wants to talk about it, but I did want to just share one thing, which is that this summer, I spent like 7 weeks in the field as part of the AROMA campaign, which is atmospheric emissions and reactions observed from megacities to marine areas. It was a NOAA-led project, but on the NASA DC-8 aircraft, which is the largest flying chemical laboratory. And although you can't see it, there are inlets all up and down this plane. It can measure basically the entire suite of chemical mechanisms. And the idea for the campaign was to try and understand high ozone in major US cities. Salt Lake City was not one of the target cities. The targets were on the east and the west coast just because they're larger. However, we were transiting back from the east coast to the west coast. We had 1 extra hour to fly around a US city, and a couple of us strongly suggested Salt Lake City. And so on August 18th, we were here for 64 minutes. I don't know if you probably didn't see us, but it's a big plane. So if you were looking up, you definitely saw us. And so what we did was we got here around 12:41. We got into the boundary layer. We followed this pathway along. We circled US Magnesium, although I will say it is currently off for scheduled maintenance, nothing to do with us. But then we came back across the Great Salt Lake and then entered right over Bountiful, and then came down the east side of the valley through the Jordan Narrows at 1,000 feet above. So if you were there, you definitely saw it. There were a lot of reports, I think. And then we circled the Utah Valley and then came back up along the western side of the valley and then did a missed approach at Salt Lake International and then climbed back out and went on to California. And we had a whole air can sampler on board. So the dots are just showing where that where a can sample was taken. So that's for extra speciation. And just to clarify, just to kind of show what the wind was doing that day, I ran 3 high split trajectories, which is a trajectory model where you start in forward mode. You start at a location and you just kind of look at how that air is moving. And so I started those models at US Magnesium and at 2 sort of industrial areas. And then the red markers are how far the wind would have been expected to go in 1 hour. So you can see that the general wind direction was coming from the south and maybe the southwest and then going up and out here. And so if you look at the intersection between those winds and our flight track, I think that we are likely to have sampled a lot of the industrial areas in Salt Lake Valley. So I'm just going to show some very, very preliminary data. It's still in-field data, which means that I can't actually show you the concentrations. I'm just going to show you the trends. And please don't cite it yet, just because it still has to go through quality checking. It will be available soon, and I would encourage you to go take a look at it. It'll be publicly available. So the first thing that I wanted to show you was I took this section of our flight track because we were circling the US Magnesium plant, and we wanted to see how that compared to what we saw before. So I'm going to show you the flight track in relative to longitude of these halogenated species as well as NOx and ozone. And what you can see here is that the only thing we saw was maybe a tiny bit of chlorine. And I did have to take off the labels, but I will just tell you that we're talking low, like less than 10 ppt. And just to remind you, during the day in Utah in 2017, we were seeing 1,000 times higher than that. So it does seem as though these are all significantly lower. There's no evidence of any of those coming above the noise for any of these other species. And also, more importantly, we really did not see any of those ozone titrations. So I have to say a couple of caveats. Is it possible that we missed the plume entirely? Of course. Is it possible that the wintertime and summertime emissions just manifest themselves very differently? Of course. Is it possible that we might be able to use this as the no halogens case for next year's summer ozone study? Maybe. We'll see.
I would even argue that 10 ppt of CO2 is exactly what we saw during winter in 2015 in the eastern US, but it's still high for the background.
But then there's also the Great Salt Lake, so it's also possible that it's a natural source. But it is certainly, we do not see the same things that we saw 6 years ago. And so then the other thing I was going to show you is that when we came down here, we sampled, there's a lot of different types of industry. And so now I'm going to show a similar plot where instead of plotting it against longitude, I'm going to plot it against latitude, and it'll look like vertical profiles, but it's just a way of saying these are the latitudes that line up with this map. So what you can see is that it was actually not a very high ozone day, but we did get some variations. But there were a number of things that kind of jumped out at us just from this 20 minutes of data that I'm going to highlight here. I think what was really amazing to see was that even at the speeds that we were going, it's really obvious when you have all of this detailed VOC information, what the different industries around here are. So for example, these high light alkanes such as ethene are sort of indicative of possibly fuel refinery. Black carbon mass tends to correlate with traffic. Ammonia tends to correlate with possibly livestock operations. There was this weird spike in CO2 that could potentially be coming from some sort of cement factory, and there is a cement factory there. There's this tracer for paints and solvents that we saw isolated from some of the other things. There's a real source of biogenics in the middle part of this valley. There's a possible tracer for plastic feedstocks. So this is, from my perspective, I think this is really cool. It's a snapshot, but it doesn't tell us everything we need to know. So I think that the instrumentation that was on here is all going to be part of the campaign next summer. We're really excited to come back, do all of these drives, and really start nailing down what the different emission sources are in this area.
Do you think there's some ozone type?
That looks like NOx titration to me. So if you plot, and this was as we were coming through the Jordan Narrows, and I think that was just the closest we got to I-15. So there's a ton to look at in here. We'll continue looking at it. Hopefully the data will be available soon. And then we're just really excited to come back next summer and see what we see.
Take a look at monoterpenes and if they line up with the ice cream at all.
I'm not sure if I looked at monoterpenes, but I definitely looked at isoprene peroxynitrate, and that did also line up. And but I'll have to go back and look at monoterpenes. There was definitely a big spike of monoterpenes as we flew over this area. So I think that's my last slide. I think I've probably been, a little bit over. But so if I know this was kind of a long talk. If there's any 3 things that I want you to take away from this, I think that from that first campaign, we learned some new things about wintertime PM 2.5 and what it's most sensitive to. And we also learned that the role of these industrial halogens is amplifying the PM 2.5, and we now understand why. We understand the chemistry of it, and it's through this VOC oxidation process. And we are really excited to come back next summer for USOS. We're going to be looking at a lot of different factors, including these halogens on summertime ozone, and I hope to be back soon to tell you about the results of those. So I think that's it, and I'd be happy to take any questions. Do you want to run the questions?
I'll ask my question and maybe run. I'm wondering if you have a sense of which VOCs contribute the most to our wintertime VOC budget?
It was, well, I'll tell you what it wasn't. it was alkenes, that was the lowest. And I think it was the carbonyls, like the acetaldehydes and the formaldehydes. So I did some sensitivity tests where I just took out different classes of VOCs and saw which one affected it the most. And it's in the supplement of my paper. I'm sort of now forgetting which class was the absolute highest, but you're right that there is a hierarchy of which VOCs, and it's just the ones that are most reactive with chlorine.
I guess my follow-up question is, what VOC halogen like mechanisms we're using? Do they tend to recycle chlorine radicals, or do they assume they're a permanent organohalogen complex that forms as a sink?
So the primary reaction for chlorine was halogen. It was hydrogen abstraction to make HCl and VOC radical, which would then become halogen. The bromine was different because its primary reaction, because it's not very reactive with, you know, the VOCs like the same way that chlorine is. It tended to react more with ozone and also get temporarily caught up in BrNO2, and it would move further downwind and then go and react with ozone again.
Thinking ahead, hopefully for Aquarius in a few winters, aqueous chemistry, how do you anticipate this might be different when we're in our lovely ice fog situations?
Yeah, that's a really good question. More surface area. That's true. So I think that was sort of an uncertainty, was that we would like to know more about how this halogen chemistry happens on surfaces, on aerosols. So I'm not sure that I know the answer of what we would expect, but I would say that the things that we would want to bring to try and understand that is more aerosol speciation, looking more at uptake rates and trying to constrain that in the model. It's those kinds of things that I think would help us understand that.
It'll be an interesting trade-off between, you've got fog, so you've got more surface area, so you can transform and you could make more ClNO2, which would produce more halogens. But if it's cold enough and it's ice fog, you don't have liquid water vapor, and you need that to do some of the activation of things like ClNO2. But that's kind of not impacted by the direct Cl2 source. So most of the reactive chlorine that's occurring, it's making this big change, is being directly emitted. It's not having to go through heterogeneous processing. So I would also say I have no idea how it's going to go. You have more surface area, but less water. So, and we don't have the chemistry on ice particles. I mean, you get in between what we know about the stratosphere, really, really cold halogen chemistry versus less cold troposphere, except it's not wet or warm. So it's kind of a big question. Other questions?
I have a question about this Fox plot. Do you not have any idea about what that plot would look like with ozone rather than Fox? Do you still see those like almost horizontal lines?
Yes, it would. So I did have that, and it looked pretty similar.
Yeah.
Yeah, so I think the other implication about that is that wintertime ozone is not really a problem right here, but if you started reducing the NOx, at some point you would also be increasing the ozone, which has its own air quality issues. At some point then you would turn the corner on both of them, and both PM and ozone would start going down, but there is a
I was wondering if you know, given everything you know about halogen chemistry and its influence on ozone. So when the state does a SIP, they have a list of species that they're looking at to regulate. Are they including halogens now? Because way back when they did the PM 2.5 SIP, halogens were not on the list. They had to work hard to even get ammonia.
good question. I think I would have to ask them.
The EPA does
The-
regulate, HCl and CL2.
Yeah.
So, and the state already has a report there, like, or the industrial groups have to report that, but I don't know exactly,
Yeah,
if the
the
state-
interesting thing is, as part of the SIP, they'll go through each of the point sources, like US
Yeah.
Magnesium, and they would like start making requirements if,
Well-
if that species is listed, but if it's not listed.
I would imagine they were, because it's not as though we came in and said, there's chlorine coming from this plant.
Yeah.
Everybody knew there was chlorine coming. Didn't say was there's bromine. And that has not been regulated, and so I think, I would guess that they're already aware of the chlorine point sources, but maybe not so much the bromine sources, because there hasn't been this historical record of them, but I am not actually sure what's said.
I'm still kind of processing. I had no idea that said about like more chlorine is produced as part of this production than anywhere else in the country combined. Is that just because of the tight? I don't even know if it produces it.
Yeah.
14% of the world's magnesium.
Is that just what it is? It looks like.
So, yeah, so actually, if you want to know, Jessica's, at this point probably knows more than me about US Magnesium, but from what I understand, it's a magnesium refinery. So what's happening is that they're pulling in salt brine from the Great Salt Lake, concentrating it, and they are trying to get the magnesium chloride or the NaCl2 from that salt, which is a minor product compared to the NaCl, but it's there. And so they are first evaporating off the water, like going through some processing and electrolyzing it to make magnesium, pure magnesium, which they sell. And then the product, the byproduct of that is CL2 gas, which they bottle and resell. But there's lots of impurities in salt water. And bromide. Yeah, bromide. It's a minor, bromine and chlorine, all the halogens exist in salt. So bromine, chlorine is the most prevalent, followed by bromine and then iodine. They're line up in the table. But there's going to be bromine impurities in salt water, and to be honest, I don't know exactly what else. They're probably going to have to explain their entire chemical process, but it seems to me that the same process that releases chlorine gas is likely to emit bromine gas and also BrCl, which is the combination of
I
those
can just
two.
imagine the Great Salt Lake being so unique, maybe there's not something like this happening anywhere else,
So-
especially like the combination of concrete.
So they mine 14% of the world's magnesium at that plant. It's the largest magnesium mine in the Northern Hemisphere, period. There's one other in Brazil and one near the Dead Sea in Turkey. That magnesium is used to make aluminum alloys stronger. So you've got magnesium in your steering wheel, you've got it in all sorts of metals that you touch every day. So it's a massively financial, like, they make a lot of money basically. They haven't had to install a scrubber. You can actually see it in the 30-year emission records of the CL2 that they've had to report to the EPA. But even when they had to install the scrubber, so did all the other industrial sources. So their percentage of the total CL2 that they emit nationwide is still 75% consistently over the last 30 years. So even though the total amount they're emitting has gone down, it's still just the largest point source of CL2. This is a really unique place and case, I will say. But a lot of what we can learn about the halogen chemistry and how it impacts our air quality here will be wildly relevant to India and China, where they still haven't installed scrubbers on all of their sources and stuff. So there are a lot of like global implications for what we learned here about it.
Definitely appreciate the overview.
So I'm not sure, this is a little bit of a tangential question and making kind of a leap from MadCorp's emissions to other things, but I did some work 10 or 15 years ago looking at chemistry, water chemistry of snow, and one of the oddest results was massive amounts of chloride in that snowpack, like on the order of 2 orders of magnitude higher than anywhere else in the world. And I didn't know about that source was that significant at the time. I assumed it had something to do with the Great Salt Lake. Now that makes me wonder. Does anything you've learned about that maybe have any relation to snowpack chemistry?
You know, I'm not an expert in snowpack chemistry, but I think so it's not as though US Magnesium is generating chlorine. They're just getting it from the salt. And I think if you look at the total, if you were to imagine the total number of chlorine molecules in what US Magnesium produces compared to the total number of chlorine molecules in Salt Lake, I would imagine it's a drop in the bucket. What's different about US Magnesium is that in the salt, it's in salt form. When they're releasing it, it's in dihalogen form, which is a massively more reactive way of reacting, of emitting it, because you expose it to sunlight and in seconds, it's chlorine or bromine particles. So, so for that reason, I don't know. I wouldn't be able to say offhand because it does seem possible to me that, you know, chloride winding up the snowpack could just be the result of a much larger pot of chlorine in a different chemical form, or it could be from this much smaller pot of a more reactive form. I wouldn't be able to say just looking at it, like what the
A couple of insights. So we saw ppm levels of HCl when we flew through the back for plume, which again, we thought our instrument was broken. We fly through a power plant plume, it's not at ppm level. HCl, the major way that it gets deposited out is through rain. So we throw a bunch of HCl in the atmosphere, it gets rained out, that's going to come out on the snowpack. We have really poor deposition data coverage in terms of the concentrations of the rainwater that gets rained out. And I had a student, an undergrad in my Atmos Chem class last semester, who tried to look at whether or not you could see a change in the chloride deposition at the local sites around Utah, resulting from the big changes in emissions from USI, but we couldn't see it at those sites. So we should talk, because I've got a whole paper about how chlorine deposition has changed over the US in time. And it sounds like you're seeing that in a way that our collection sites just are not in the plume path to be impacted by this. So what goes up has to come down. If they're taking the salt in the lake and throwing it into the atmosphere as a gas, it's going to eventually come back down to the rainwater. So.
But whether it happens here or in Colorado or
It's just like from like the atmosphere before it rains out. So.
Right, I mean that could be also part of it. I mean your PCAPs get cleared out by snow.
Yeah.
So
And with that, I guess we'll thank our speaker.